warm welcome from my side to a new edition of our Partech Virtual Talk series. And today our general theme is future energies. It's great that you all join us to learn how to produce raw materials safely, sustainably, and with a good CO2 balance. At Partech in autumn, there will be further expert exchange on our key topic, so stay curious. Experts from re-owned Partech exhibitors will support us today and show you the latest developments. And before we go into this topic, I would like to thank our speakers, Michael Wetzel from Industry Manager Batteries from ATSO, and Mr. Dr. Stefan Gerl, Head of Process Technology Test Center from Maschinenfabrik Gustav Eirich, and Mrs. Dr. Jennifer Burt, Applications Specialist from Malvern Panalytical. Without them, this would not be possible. And now I hand over to Michael Wetzel from ATSO and his talk about safety sustainability, challenges for the handling of battery raw materials. Enjoy the talk.
So, thank you for the introduction. Good afternoon, everyone. It's a pleasure for me to join this virtual talks. And as already announced, my topic today is safety and sustainability, challenges for the handling of battery raw materials. A short look at the table of contents. So we start with a very short introduction of the company ASO, followed by an overview of the ASO portfolio. Then we'll have a look at the different battery raw materials and their properties, as well as the specific challenges for handling of them. In the next chapter, we show diagrams of different raw material handling concepts, state-of-the-art and alternative improved concepts. And then we'll finalize with an overview of the material handling in future gigafactories and our concepts for more sustainable material handling using dositainers or batch tainers. So the company ASO was founded in 1949 by the family Zimmermann. So next year we'll have our 75th anniversary. And the foundation stone of our headquarter was done in 1963 here in Osterburgen. In our headquarters, we employ approximately 700 people worldwide. We have more than 1,000 employees in 9 ASO group companies. And the turnover of ASO is around 180 to 200 million per year. So ASO is a specialist for raw material handling and automation. Our scope of supply starts with the storage of raw materials after delivery. And from the silos, we provide the discharge equipment, devices for feeding and screening, loading and converting. The dosing and weighing equipment is feeding the core process here in the center of this diagram. This could be a mixer, could be an Irish mixer, or could be a mill or a reactor. And this is, of course, this core equipment, this mill or mixer is not our scope. After this process step, we take over the material and feed it to further process steps. And of course, we can also provide the operating and controlling of the whole process together with the monitoring and documentation of the process. I would like to show some photos of typical ASO equipment. So as already mentioned, we can provide silos for storage of material. We do the product feeding out of big bags or out of bags with special devices. We can convert the bagged material from big bags or bags again to containers or batch tainers. We can do the automatic assembly of batches in small quantities or also in big quantities. Our core competences, of course, are also dosing and weighing. So we manufacture the screw feeders, the weighing equipment. We do all kinds of feeding and cyclone screening. We can provide solutions for pneumatic conveying. It could be suction conveying, dense phase conveying, all kinds of pneumatic conveying. And as mentioned before, we're very strong with controlling and automation. And tracking and tracing is a very important issue, especially for the battery industry. And of course, we provide the visualization systems and the collection of data. So before we start with the design of a material handling and dosing system, we have to characterize the material properties. And I would like to show a short movie which shows the process and the classification of raw materials in different groups. So we've classified them in 5 groups. And
we love ingredients.
This movie shows it shortly.
All raw materials have their own individual properties and characteristics. Our knowledge of physical analysis is one of our core competencies. No matter how differently ingredients behave, we master them all. There are highly flammable, challenging raw materials, the divas. Others are difficult to control, free-flowing and dusty, the free spirits. Some raw materials are sensitive and fragile, the weaklings. There are obstinate ones. They tend to cake and flow poorly, the stubborn brats. And very particular raw materials are abrasive or toxic, the meanies.
Okay, so this was a short overview about the different characterization of groups of raw materials. And now we'll have a look at the battery raw materials, and we'll see that some of them also belong to the, I would say, unpopular products like the meanies, which were mentioned as last group. So in all battery factories, we have an anode and a cathode line. And we have active materials, we have binders, we have conductive materials, and sometimes additives. The active materials for the anode are mainly graphite, also silicon, could be share of 5 to 10% of silicon. For the cathode, we have many different chemistries like NMC, LCO, LFP, and so on. And also different grades or of these chemistries. For NMC, for example, could be 622, 811, and so on. For the binders, on the anode side, we usually use CMC as a binder. For the cathode, typical binder is PVDF. If we have a look in the future, for example, for dry mixing and dry coating processes, the PVDF, for example, is replaced by PTFE binder, which has some special characteristics. The conductive material is always conductive carbon and quite often carbon nanotubes also. These carbon nanotubes are sometimes added as a powder or already prepared in a slurry and added to the mixer. There are few additives. Typically one is oxalic acid, but this is not used in every factory. Okay, so if we have a look at these powders, they have some typical properties. So the powders are usually very fine, they are dusty, most of them are black except for the binders. And for all these powders, we have to care about operator protection. Yeah? Most of them are not hazardous except for the cathode active materials and some carbon nanotubes, for example. But at least we also have to consider at least the OEB1 or sometimes OEB2 level for these powders as operator protection. There are some special materials. I already mentioned this PTFE. This PTFE, for example, is very sensitive against shear and against high temperature. Yeah, so sometimes it's a challenge to cool the material already during storage and to avoid any introduction of shear strengths, because the fibrillization of this PTFE should be done later in the next step. For example, an Eirich mixer, which is especially suited to open and fibrilize these PTFE fibers. And so we have to care about the process protection. And the most critical materials, as mentioned before, are these cathode active materials. So there we have the issue of operator and the process protection, because this cathode active material is always very heavy. So we talk about a bulk density of 2 to 2.5. It's often sensitive against moisture, and at least all NMC-based or LCO-based materials are hazardous. Only LFP is not so critical. Yeah? So the operator protection is on a higher level here for these materials. Okay, so now I'd like to show you a diagram with a typical arrangement for a gigafactory, let's say 6 or 10 gigawatt hours. So this diagram shows a combination of a pneumatic system and a gravimetric feeding system. So the materials, the smaller amounts like the binders and conductive materials are delivered in bags. Then we have these bag feeding stations here, and they are feeding the material to loss in weight feeders. If it's an ASO product, it's a so-called ASO-DOS system. And for the active materials, which are necessary in higher amounts, we usually have the big bags here. And for such a combined system, we often have a big bag station on one position, and then we have a pneumatic conveying, usually a suction conveying to a separator, and then feeding again a scale, which is feeding to the mixer, which is not shown here. So this is a state-of-the-art system, which is also used in Asia and also in the Asian companies which are manufacturing in Europe presently. And it has some advantages and disadvantages. Advantages are it's quite flexible system. So especially for this active material, you can place the big bag discharge system, let's say somewhere on the ground floor, and then you can suck the material to 1, 2, 3 mixers somewhere else. So it's flexible. And you usually don't need so much height for the system because it should be a 2-story building, a ground floor for the mixers and the first floor for the dosing and storage. The system also has big disadvantages. So the footprint is quite big for such a system. The cleaning is sometimes an issue because if you have pneumatic systems, you have to clean pipes also. And the operation costs have to be considered because if you have a conveying system, sometimes you have to use dry air. If you have critical active material, cathode active material, you have to do maybe the pneumatic conveying even with inert gas. And this is a high cost factor. Yeah? So this system could be quite expensive regarding the operation costs. Okay, now I would like to show some short animations about this core equipment in such a plant. So this is a principle of a back feeding system. So you can show we have this hopper, you open the flap gate here, then you empty some bags of binder or conductive material, and you have a storage system here, and then you feed the next step, which is the ASO-DOS, the loss in weight feeder. And during feeding, the filter system is working. When the feeding is finished, you have a closing cleaning cycle, and the material which was sucked out falls back to the hopper, so you don't lose any material. So from this feeding station, you usually feed such a loss in weight feeder. This is an ASO-DOS, so-called ASO-DOS system. And the working principle is you can use it for batch process as well as for continuous processes. If you have a batch process, it's quite simple. You have a gravimetric system, a load scale, and you weigh the material which is fed to the next process exactly. If you have a continuous process, you have the challenge to refeed this material during the process. And usually the solution is that you do a gravimetric feeding during 90% of the cycle. And when you refill the scale, you have to stop the gravimetric feeding, and then you do a volumetric feeding for, let's say, 10% of the time. Yeah? So this is a well-established solution for such a system. Okay, so this is now, again, a diagram of the same system, but for the cathode here. And on the cathode line, we have another challenge, because for the cathode, we have this, you can remember, this cathode active material, which is often hazardous. And in this case, we have a challenge to minimize the dust exposure and reach a higher OEB level. So usually it's requested to have an OEB3 level to minimize the dust exposure to the operators. And for such an OEB3 level, we have developed a special big bag discharge system. You can see it here. And I would like to show a movie showing the principle. I will stop speaking during this movie because it's self-explaining. So the principle is written down during the movie. Oops, sorry. Okay, so with regard to the time, I stop here because we just show some more options. But if you're interested, we can provide some more information. Okay, so I would like to proceed now with a diagram showing an alternative concept. Generally, it's the same from the raw material delivery. We have the smaller materials in bag, the active materials in big bags. And the difference is we have a pure gravimetric system here without any pneumatic conveying. And you can also see that we have one raw material feeding system, which is providing the raw material to two mixers. So with a scale here, with a two-way distribution system. So this is quite economic because one powder dosing system for two mixers. And the advantages compared to this state-of-the-art system, this combined system, is the footprint of such a system is smaller. The operation costs are lower because we don't have to provide any dry air or even nitrogen for feeding or for transporting of the material. Of course, we have also some disadvantages. So the flexibility is a little bit limited because we just can provide the raw materials to two mixers. And of course, we need a higher building. This is usually a three-story building. We have the ground floor with the mixers. We have the first floor with the weighing and dosing systems. And we have the top floor, which is already the third floor or second floor for the raw material discharge. Okay, this is now a 3D layout of a system which we have realized together with the company Eirich in Asia. So the capacity of this gigafactory is already 5 gigawatt hours. It's, as just explained, a three-story design. We cannot see the mixers here. So this is the ground floor with the mixers. This is the first floor with the scales and the loss in weight feeders, the ASA-DOS. And on the top floor, we have the material feeding system. So in this case, we don't have a two-way distribution. We have a movable scale. So theoretically, it could be also possible to extend the plant by a third mixer, because with the scale, we could also feed 3 mixers. Okay. At a certain stage, we are limited because you have to do the dosing, you have to distribute the material, but 3 mixers is generally possible. Okay, so then I would like to proceed with an animation, which is not made or not for a battery industry, but just to give you an idea how the system of a distribution from one raw material feeding line to several mixers is possible. Yeah? So you can definitely see this is not a battery line because there are so many raw materials in this case. Also, the mixers which are shown here are not suited for battery production, for slurry production. This is more for dry processes. But I just want to show that with such a system, with a circular, with such a loop, it's possible to feed several mixers with one dosing system. Yeah? So we have to use some feeders. The number of feeders depends on the number of mixers, and of course also on the batch times. So in this case, we have quite a lot of feeders because this should be a simple process with very short batch times. And then you maybe need 2 feeders for 1 mixer. In the battery industry, it's quite different, because if you consider this old-fashioned technology of planetary mixers, the batch times are several hours. Even if we go to the fastest system on the market, the Eirich mixers, we talk about batch times of maximum or 20 minutes to 30 minutes. But using such a concept would be possible. So we could use, for example, 2-3 mixers with 2 scale systems, yeah? Or even more mixers. So this just to give you an idea. And we are working on such concepts, especially with fast mixing systems in this industry. Okay, so now I would like to draw your attention to sustainability, especially reduction of waste. So this pie chart shows the battery production beginning of this year, let's see, end of 2022, beginning of 2023, and the forecast for 2030. So, and I've made it in different regions. So as you can see nowadays, nearly 75% of the batteries produced worldwide are produced in China. The share of Europe is approximately 16%, which is actually 120 gigawatt hours per year. If we have a forecast for 2030, so this amount in Europe will nearly increase by factor 10. Yeah. So, and I would like, regarding this calculation of big bag and waste, I would like to focus only on Europe here. So based on these numbers, which I've just shown, I've made a calculation about the waste which will arise. So, and again, I only focus on Europe, and I only focus on big bags for cathode active material and only cell manufacturers. Yeah, just to give you an idea, it's only a small portion of the whole industry. Yeah, and so I've calculated based on the gigawatt hours today and in 2030. I've calculated the cathode active material throughput in the plants, and based on these throughputs, I have calculated the necessary amount of big bags to fulfill these requirements. And this is the calculation in big bags per hour, and this is the calculation in big bags per day. You know, the production in such a lithium ion manufacturing facilities is 24/7. And the result is, if you take an average weight for a cathode active material big bag with inliner, we produce today between 5 and 10 tons per day of this hazardous waste, only with big bag material, with inliners. And this will increase until 2030 to 50 to 100 tons per day of hazardous special waste, only for the big bags and only for cathode active material. Yeah. So, and again, this calculated waste is only for cathode active material at European cell manufacturers. If you consider the whole supply chain and not only the cell manufacturers, this will multiply, because the big bag is already used in the cathode active material production facility, and so on. And so this is only this 100 tons, which is a tremendous amount already, is only a small portion of the total amount. And we also have the anode active material and so on, which is of course not so hazardous. So based on these numbers, our idea is to use containers or dositainers quite early in the supply chain. Yeah. So our idea is to have cathode active material manufacturers which fill the material directly to batchtainers or dositainers. And this animation shows the process of filling of such a batchtainer. So you transport such a container, let's say with a volume of 1 cubic meter or even bigger, with an HEV or a forklift to the filling station. You place the container usually on a scale, and then you connect. You connect it with the filling flap, which is pneumatically driven. So to give you a better idea about the process, I have this movie. This is such a filling station with a split valve technology. So this means this is used for OEB 3 level. So on the container, we have the passive part here. This is the passive part of the split valve. And the active valve was lowered by pneumatical cylinders. Then it's connected and the flap was opening. So now this is in our workshop, it's not in a production facility. Now the filling of the container would start. And after container is filled, just go ahead with regard to the time. After filling of the container, so we close the flap and we lift the active valve again with the pneumatic cylinders, and then the container can be taken out from this feeding position. And this is completely dust-free system due to this split valve technology. Okay, so the next step, now the container is filled. That could be in the workshop of a cathode active material manufacturer. And then the container is transported to the cell manufacturer. And at the cell manufacturer, we have a discharge station. This is shown in the animation here. There are also different solutions for discharge stations. This is a quite complicated one with a roller conveyor. Could also be simplified with just with forklift or with HEV. So in any case, you have to transport a container to the discharge position. I have some problem with the movie. Okay. The container is lowered. So the split valve, active passive valve, is connected. Then we connect the compressed air. So in the next step, we do the docking of the drive for the screw feeder. So the screw feeder is without motor, a part of the dositainer. And now we do the docking of the drive of the screw feeder. We open the screw, the cone at the end of the screw, and we open the split valve. And now the dosing of the material is done to the follow-up process. So with a dositainer, we don't need additional scale because this is installed on a scale, and we do exact dosing to the next process step. Okay, so this is now such a station showing a feeding position. So here you can see these are the discharge stations as loads with load cells, and you would place these dositainers or containers in the stations, and you can feed directly to a mixer. So in this case, we have shown an Eirich mixer, and this is our idea for very sustainable, efficient material handling. So if we can convince the raw material suppliers and the cell manufacturers to establish such a supply chain, it would make the raw material handling much more efficient, safe, and sustainable. And it has many, many advantages. Of course, we have to also mention there are few disadvantages because the initial cost for such systems are slightly higher compared to a state-of-the-art system with this gravimetric feeding or combined gravimetric and pneumatic feeding. And the other challenge is it doesn't make sense if the active material supplier or the manufacturer is in Asia. So the transportation, the distance has to be quite short, but this should be solved in future because more and more active material suppliers will establish their workshops quite close to the gigafactories. And so if the distance for transportation is quite close, this will be definitely the most efficient, sustainable solution for this raw material handling. So at this stage, I would end with my presentation, and I hope I'm still in time and looking forward to your questions. Thank you.
Thank you very much. So we just have a look at the questions, and there are some. Michael, what UEB level can be realistically achieved with ATSO equipment? Which plant components or process steps, for example, filter change, cleaning, etc., pose the greatest challenge in the terms of OEB? That's one question.
Okay. So as a single unit, we can provide OEB 3 level. As a system, we can even reach higher OEB levels. So using this OEB 3 station in a cabin with a safe change filter system and with a big bag discharge system, we can also reach OEB 4 level. So at the moment, as I said, we can reach OEB 4 with a system, not with a single piece of equipment, but with a system, we can reach OEB 4 level. And the challenge for contamination, if you watch, for example, the big bag discharge station, the most critical part is to take the big bag from the station, because there's always a risk of some material dropping down. I hope this was the answer.
Thank you very much. So then we have a further questions. Are there uniform standards regarding containment, or do cell manufacturers have differing guidelines?
This is a good question. So it's always surprising for us after quite a long time that we have many different standards or requirements from customers. So, okay, if we watch Asia and even the Asian manufacturers in Europe, they have, according to our information, quite low requirements or OEB standards. With all European manufacturers, which are in the focus in future, we are talking at least at OEB 3 standard, but still there are many differences. So some, they only care about clean equipment regarding the non-hazardous material. Others, they require, even for the non-hazardous material, they require OEB 1 or OEB 2 level. But again, there are no standards. So everybody is sometimes are copying others, but we cannot see that there are real standards, which is still a surprise for us after such a long time.
Thank you. So there's another question. Are these projects executed by a general contractor slash EPC contractor?
Okay, depends. So we have all kinds of projects. Sometimes we are in direct contact, so we are supplier to the cell manufacturer, to the active material supplier. In other cases, we are part of the so-called slurry preparation project. This is often the mixer supplier. Yeah, so could have project with Eirich, for example, as a mixer supplier, which is the core process. And okay, we could also work with EPC contractors. Yeah, so all kinds of contracts are possible.
Okay, then we've got last one question. How would you combine volumetric system like rotary valve with weighing cells?
Volumetric is okay. We don't use volumetric system. We only use gravimetric system. Yeah, the volumetric dosing is, or the volumetric systems like a rotary feeder is only used in combination with, let's say, a loss in weight scale, for example, or for feeding of a system. But for all powders, we only use gravimetric system. Maybe this was confusion. I just explained this volumetric dosing is only done during a short time in this ASO-DOS if you have a continuous process. Yeah, but since we have usually batch processes in the battery industry, we don't have any volumetric dosing. It's a pure gravimetric dosing.
Okay. Thank you very much for this very interesting presentation, Michael. In case you have further questions, dear participants, please don't hesitate to contact us via email at pautech@nürnbergmesse.de, and we will forward your questions to Michael Wetzel. Thank you very much.
Thank you and goodbye.
And yeah, we will continue directly. Our next speaker is Dr. Stefan Gerl from Maschinenfabrik Gustav Eirich. And his topic is cost-effective and CO2-reduced LIB electrode production with innovative mixing technology. Dr. Gerl, the stage is yours.
Marina, thank you very much for the kind introduction. Good afternoon, ladies and gentlemen in the web. The title is mentioned already, so I jump in directly. Eirich is even a little bit older than ASO. This year we have 160 years anniversary, a family-owned company similar to ASO. And we are dealing in lots of different industries, but mainly in the lithium-ion battery application. We have different application or areas. This is the upstream raw material preparation for the active material, like cathode active material, mixing of precursors and functionalizing, means coating with nanoparticles, for example. We have then on the anode raw material side, we have production of synthetic graphites by mixing of carbon, coke and pitch, which is then graphitized into synthetic graphites. More and more often customers are using our technology then for the silicon carbon composites, means it could be a coating like in the cathode active material, but it could also be incorporating silicon particles into a powder mix, which is then synthesized to a silicon carbon composite. But today we want to concentrate on electrode production, where the classical electrode production is made wet, means we have to produce a coating slurry out of the powders. Then we have some, let's say, special applications. We call it semi-wet, where we increase the solid content significantly. Typically, the forming is made by extrusion. And last but not least, the, let's say, now upcoming process is the complete dry application, where we have to produce a structured dry mix with calendering and pressing, and last not least, then winding. Eirich is not just providing the mixing technology. For example, together with ASO, we also offer a raw material handling, the complete weighing and dosing system. We have our own know-how from many, many industries, so that we know how to design such dosing systems and how to control such dosing systems. And this is also at the end, the heart of the complete solution, that we have our own control systems based on Siemens 7 systems, so that we can offer a turnkey solution around the complete powder handling and electrode product preparation. As I mentioned, today we want to focus a little bit on the wet side mainly, and then last but not least also on the dry side. Eirich invented the first mixers in 1903. The planetary mixer was invented in 1907, and we have operated these kind of machine with static mixing chamber and eccentrically tool, but moving around a planetary axis and a sun axis from 1907 on, learned the pros and cons, and out of this we developed the so-called Eirich mixer with rotating mixing chamber and eccentrically mounted mixing tool, which is so superior in capacity and performance to the planetary mixer that we stopped manufacturing any other kind of mixer. We have only one solution, which is so flexible that we can, let's say, master almost every application. How does the mixer looks like in detail? As I mentioned, we have a rotating mixing chamber, which is taking care of the transportation of the material. So if we have a static mixing chamber, like in a planetary mixer, the mixing tool has typically two tasks. First of all, transportation of the materials. Secondly, then the mixing. If you increase the speed of the tool, then typically the transportation collapses, because by centrifugal forces, everything is pushed to the outside. This means typically these kind of machines with static mixing chambers has to run on a reasonable low speed, which is not good enough to disperse and dissolve fine aggregates like the additives like carbon black or nanoparticles. So that at the end, they need a second DESPA tool to make this job. And in the Eirich mixer, the movable or rotating mixing chamber takes now care on the transportation so that we can work independently with our eccentrically mounted mixing tool. So we are free now to choose the shape of the tool. We are free to choose the speed, which can be very gentle and soft, or very aggressively. We typically operate our machines up to 30 meters per second. For dry battery application, we can go even up to 45 meters per second. And this not only in the small scale machine, but also in full scale production machines. We have a static wall and bottom deflector or scraper, which was made really scraping for the battery application to make sure that we have no powder or plastic body adhesions on the wall or bottom, to be sure that 100% of the solids are really incorporated into the final slurry. The original mixers were all horizontal. In the 70s, Eirich started to incline the machines. So if you have a look onto our webpage, you see lots of machines with a 20 or 30 degree inclination. But for the battery application, we moved back to the horizontal. First of all, a liquid will not flow up the hill while moving. Secondly, the cohesiveness of these ultrafine powders are forming typically wavy material flow inside of the machine. And by the horizontal machine, we can make sure that we have an even distribution and no problems with material leakage out of the machine at any point. For almost 100 years, we don't had any double jacket cooling system because it was not necessary. Our systems are so energy efficient that you don't have a significant heat up of the material. Or we have then developed vacuum technologies for evaporation of cooling, of liquids for cooling, like in the foundry industry or in the lead acid battery application. But the customers in the battery industry force us to introduce a double jacket cooling system so that we have now machines available from lab scale 5 liter up to full scale production, which is today a 500 liter machine. We have developed in the 90s of the last century the vacuum system. Means we are putting the rotating mixing chamber into a pressure vessel so that we can apply vacuum parallel to the processing. This means we can produce a bubble-free coating slurry during operation while applying vacuum. We have typically a discharge system in the concentrically in the center of the mixing chamber to save height and also to be more flexible with the cooling systems on the complete bottom of the machine. We have designed special discharge systems either for the liquid slurry or also for the structured dry mix you will see later on. For a fully automated plant, we offering also high pressure liquid injection systems, which are used in 2 ways. First of all, you can, of course, do a washing out of the machine for an automatic cleaning. But more important, we are adding the liquid we have to add anyway into the slurry over these, let's say, different kinds of rotating and static nozzles to make sure that we are washing away always all material which might stick on wet surfaces, like when you're charging the powder and you have a wet cover of the machine, to make sure that 100% of the solids are really part of the slurry and we don't have to interrupt or to stop the machine for cleaning. By this, you can save a hell of, let's say, cleaning liquid, because we hold the machine always clean, already clean over the batches, and can make sure that by batch to batch operation, like in the gigafactories, we don't have any changes between the different batches. How is our philosophy in mixing? Typically, for the planetary mixer, you have to prepare a binder solution, which takes already sometimes a day. You have to add PVDF into NMP or CMC into water. And our philosophy is coming from the ceramic industry, used already since decades in this industry. So we said we add all dry powders, all dry materials like the active material, the conductive parts, and the binder. We are doing an initial short, intense dry mix, typically 1 minute, to make sure that first of all all, let's say, components are homogenized properly. The binder is separated from each other to prevent any jelly structures when adding the liquid. And we are dispersing already the carbon black to some extent. You will see later for the dry battery application, we run this a little bit more advanced. For the wet application, it's already good enough to run for 1 minute. After this, we are adding a first portion of liquid, typically around 50%, to reach a full plastic body, which is always named in Asia as a hard kneading. Within this hard kneading phase, we are solving, first of all, the binder, and we intensively shear the system to disagglomerate, to wet, to disperse the carbon black to form a good electrode network. And this is also the point, you can need a certain minimum shear rate, but we see that after roughly 7 minutes, we achieve already a so good quality that we have a properly dispersed active material, we have a properly dispersed carbon network, and we can reach a good coating slurry. So after this most important kneading step, we are then just adding the missing liquid, which takes typically 2 to 5 minutes. When we are going for a complete water-based system, like for anode, where you have then a liquid binder like SBR, we are adding then the liquid binder like, let's say, cream into coffee at low shear rate, so that the overall processing time typically takes 15 to 20 minutes, and this is almost the same for anode or cathode. Anode is a little bit maybe longer because of the SBR addition. The overall batch time, this means from in to out, we are actually calculating between 30 and 40 minutes, depending on the filling of the machine, because the extraction is taking a little bit more time than in the past with our concentric discharge systems. The advantage of the system is that you can adjust all the parameters like time and shear rate. In every phase, you can even make sub-phases within the kneading phase. We have an additional possibility because to measure the viscosity like a viscometer inside of the machine, as our tool doesn't let's say contact bottom or wall, we can stop, for example, the mixing chamber, start rotating the mixing tool at defined speeds, and then measure the torque, and by this we get a response like within the viscometer. This helps us to, let's say, qualify already the slurry before we are discharging it into the downstream transfer and storage tanks. The inline viscosity measurement can be made at the last, or of course in between. It could even be repeated several times if necessary, to qualify the slurry before discharging. We have different options. With a non-vacuum machine, we typically then apply a vacuum in the storage and degassing tanks downstream of the mixer, which is a little bit the cheaper version. Some products don't need vacuum application during operation. On the other hand, with our EVAC mix vacuum technology, we apply vacuum in the final phase of the first liquid addition, doing the kneading already under vacuum, so that we don't incorporate any gas or air already from the very beginning. And by this, we can make sure that we have a 100% degas slurry already at the final stage of preparation. I have to switch one back. Here we see a view into a full-scale production machine. It's a 500-liter R12 mixer. You see the different phases. So on the lower left side, you see the kneading phase, the plastic body moving at high shear rates through the machine. Here you have then the final slurry after liquid addition. You see the clean walls, which is coming from the effective wall scrapers. And here during discharging of the slurry, and at the end, we have a very thin layer of liquid, let's say covering, for example, the mixing tools, but this isn't interrupting our process. So if we are working in a gigafactory batch by batch, this is good enough to prevent any problems in repeatability. And by this, we can make sure that we have a high output out of a very small machine. Lots of customers are asking for continuous process because, of course, the continuous systems have some advantages in view of the customer. But on the other hand, you see at the end that also a continuous system like twin screw extruder, just the mixer itself and maybe part of the dosing system. And as Michael Wetzel explained, has to be, let's say, changing over from gravimetric to volumetric in between is really continuous. These are the green parts. And you have lots of equipment like powder dosing, pre-mixing, binder solution preparation, and of course also the degassing and storage tanks between the mixer and the coater as a batch-wise operation. This has also to do with the fact that no operating company in a gigafactory would allow to apply directly out of the mixer without qualification and without any buffer tank directly onto the coating line. Eirich has a quite similar solution. We call it Conti feeder. So we have an automatic batching system, which is even more accurate because we can control and we are extremely highly flexible in changing over the recipes. The material will be then collected in a balance or charged directly into the mixer. Then we are starting our batch process like shown before. And then we go into also a series of tanks. Typically, we have one tank which is directly, let's say, connected to the mixer itself, which has the same volume. By this, we are sucking out the coating slurry. With vacuum, we can qualify it. We can take samples. We can put in these systems with return pipes, also additional sensors. And if this, let's say, batch is qualified by the operator, we are sending it into buffer tanks, which are then connected directly with the coater, so that we have also a continuous supply of the coater, which is the most important part for the customer. All of this can be fully automated, starting with barcode readers for the raw material or QR code readers for raw material identification. We are monitoring all the data coming from dosing systems. We have the mixer with motor power, energy, temperature profile. We measure the viscosity with our inline rheometer. We have the same data out of all the tank systems, which is all collected with our PLC and can be visualized with our ProView system, which makes it easy to compare also different batches to set trend curves or tolerance bands to allow monitoring, inline monitoring of the production process. We are offering these data collected, of course, can be used then for data mining or artificial intelligence methods. And we are offering different, let's say, versions starting from, we call it QualiMaster LIB, from ECO, which typically means OPC UAA communication with MES systems. We have the QualiMaster ProView for data, let's say, trending. We measure product temperature. We have the inline viscosity measurement, which comes anywhere with the machine without additional, let's say, equipment. Measure motor power, energy. And if you want to have more, we can, of course, add lots of sensors like viscosity and density as inline sensor, or even up to particle size distribution and concentration, which is at the end just a question of money. This graph is now showing out of a full gigafactory scale, a 5 gigawatt-hour factory in Asia, how good is the reproducibility of our system. So we made for SAT 10 directly consecutive 420-liter batches. And you could see that this mean value for the solid content is quite low. The standard deviation is quite low. This is mainly attributed to the dosing system, either the powder dosing or the liquid dosing, of course. The same is for the slurry density, because this is mainly affected by the dosing system, like the solid content. And the viscosity is also in the very narrow range. The upper and the lower, let's say, black line is the typical, let's say, upper and lower limitation of the coater. And we are sitting in between, and we have an excellent reproducibility batch by batch. How different gigafactories could look like. So we have different concepts. One is, let's say, for low capacity applications, typically in the range of 0.5 to 3 gigawatt hour. which means at the end we have one mixer which is located on the ground floor. We have, as Michael, let's say, shown before, we have a 2- or 3-story system. On the top level, we have the back and big bag handling station. We have a second floor with the automatic dosing system to achieve the necessary accuracy and powder dosing. And we have all liquid dosing system and liquid transfer system then on the ground floor together with a mixer. Another project or a size is then a 5 to 6 gigawatt-hour factory with 2 machines in parallel, also like shown by Michael, Wetzel. This this 3 level system on the top, again powder back and big bag dumping station. Then the dosing, and we have then the distribution system between the 2 machines. It could be a valve, or it could be this movable, let's say, container. This is then the option then with 3, and we can go up to 4 machines in a row. This means you're using really the dosing system in the best way, and then distributing between the 3 or 4 machines, which are then working more or less in parallel. By this, we can reduce, of course, the footprint dramatically. And of course, even if the height is a little bit higher than, let's say, with a pneumatic system, we are still much lower in height compared to these extremely big planetary mixers. There's a view into the UK big pilot facility where Eirich and ESO has, let's say, delivered the machines. The complete control system is coming from Eirich. So the heart is, of course, the R12 mixer. We have then the ESO DOS systems here directly mounted on top. We have the liquid distribution and dosing systems for small amounts like SBR, or the high amounts like NLP or water. And we have here, we call it batch pure, the movable transfer tanks. This means these tanks are connected to the mixer, filled with a slurry, qualified, and then they are moving it manually to the next door. This is a top floor with glove box system, with sack dumping station, with inline sack compactors. And here we have, for example, with a big bag station for graphite, then also the dosing system. What is, to give you an overview about, let's say, a little bit the energy consumption and size of the machine. And I want to compare this with extruders and the classical PD mixers. So even if PD mixers are quite big, typically they have 1500 liter, 2000 liter, up to 4000 liter even. And if you use just 80% of it, this means in a 1500 liter machine, you can typically produce 1200 liter of coating slurry. But because of the long mixing time, typically 6 hours, you have an output which is just in the range of 100, maybe 150 liter per hour. So this means at the end, if you want to go into gigafactory scale, you need a huge number of machines operating in parallel, which is, of course, then the problem to distribute also all the raw materials and also to collect all the final slurry from the machines. On the other hand, we have the extruders, which have a retention time, which is in the range of 1 to maybe 10 minutes. They can produce an output which is in the range of, let's say, small to medium-sized gigafactories, depending on the size. But they are limited in flexibility, because if you want to change over the product, then you have also to change the screw, for example, or screw geometry. The Eirich mixer is capable to run in a wide field because we can control the batch size, we can control the batch time. If we don't need so much high capacity, we just make 1 batch an hour instead of 1.5 or 2 batches an hour, and just wait in between until the next batch is necessary. But by this, we can make the same quality. A typical plant with 1 R12 mixer comes into the range of 3 to 4 gigawatt hour. This means if we want to, let's say, design a plant with up to 10, 12, 16 gigawatt hour, we are just put 3 or 4 machines in parallel. And if we have a view onto the energy consumption, then you can see that there's a big difference, and this is at the end the cost saving. So a typical PD mixer with 1500 liter and 1200 liter has an installed power of almost 300 kilowatt. with 6 hours mixing time, and having in mind that maybe just 80% of the total or the maximum power is really used, and overall roughly 40% as a mean value, we have still an average of 96 kilowatt, which means or is ending up as 480 watt-hours per liter. A double screw extruder roughly needs 100 to 160 watt-hour, which is quite significantly lower. And this gives you also the opportunity to save. With the Eirich mixer, you can go down even more. Even if we have big motors like 60 kilowatt for rotor and mixing chamber, we have just this very, very short peak where we need this extreme high motor power, and then we are falling down again during the kneading phase. This means we have just an average of about 12 kilowatt, ending up with about 16 watt-hours per liter. This means we are saving here in comparison to PD mixer more than 90% of the energy. What does this mean in view of costs? First of all, of course, we have the cost for the electricity. And we're talking here about gigawatt hours of electricity. For a 20 or 50 gigawatt hour plant with about 3,000 liter capacity. This means for a PD mixer, we have already 20 gigawatt hour on electricity we need to operate these machines. On top, we have the energy consumption for the chiller, because you could imagine that 90% of the energy we are using for moving the material it's not used really for mixing or dispersing, it's mainly used for friction. This means it's heating up the material, and this has to be compensated by a chiller, means you have to put on top minimum the same amount. It's even higher because of the lower efficiency of the chiller itself. At the end, we have then additionally CO2 emissions we can calculate. At the end, we have a huge cost block, for example, for the PD mixer in total on electricity costs and CO2 certificates, which has to be paid for the European community, European Union, for example. So at the end, you can save 6.3 million euro per year just by using a different mixing technology. This is the advantage which is coming then in view of the building. As I mentioned, typically also a planetary mixer facility has a two-story. The first floor is between 12 and 16 meters height. The second floor is about 10 meters in height. We need for this capacity roughly 12 machines. You see these has a footprint of 5 by 4 by 6 meters height. And a total installed power of about 350 kilowatt. And we can do the same with an Eirich mixer, 2 lines in parallel with 3 machines each. This means we have a total, let's say, space, which is just 20% of the space necessary, the ground floor space, which is necessary for the planetary mixers. We can put the complete system in, let's say, 2/3 of the height of the building, which means you can reduce the building height and the building size by itself. And we have, of course, much lower installed motor power, which is also beneficial for the supply. The next technology to save even more energy and CO2 emissions to make it more sustainable is then the way, let's say, or the transfer from the complete wet application to the dry application. And here I want to show you the differences in the application or in the complete electrode production. So typically you have then the mixer, you have the powder handling and dosing system. You have, of course, fresh solvent, and typically also use recycled solvent, which is coming in gigafactories out of an own recycling plant. The slurry is transferred into different tank systems to used as buffer and to provide different coating heads, typically as on a tandem dry or tandem coater, where you have 50 to 100 meter in between the two coating heads. You have then the drying air generation, which can be a gas burner, let's say, or oil burner. And of course, you have an extremely complicated exhaust air treatment system to get out the evaporated NMP out of the air stream. This is condensed, and then of course you have to recycle it, that you can reuse it together with fresh solvent. Then typically, of course, you should know calender and slitter, vacuum, coil drying, and then cell assembly. And for the dry application, we can cut down all this yellow marked equipment. This means we still need, of course, powder handling and dosing. We still have a mixer, which is preferably the Eirich mixer. We need then additionally a powder transfer and dosing system, because now, while we had pumping here with let's say liquid pumps, we need different technical solutions for transferring the material to the dosing line, or the dosing system, which is feeding then, for example, the calendar. We have still a vacuum drying system, which can become smaller because we are not bringing in any liquid which has to be evaporated, just the humidity which is coming with the material, and then the cell assembly. And you could see already on the size of the equipment that this can be reduced the building structure significantly and the cost for operating dry rooms. The Eirich mixer is now capable to run also, let's say, with this kind of electrode. We are working a little bit in a different way. First of all, we are we add carbon and active material. It could be cathode or anode active material. Then we are typically coating the active material. This means we are dispersing the carbon black in the way that it's really sticking on the surface of the active material. We can see this, whether we have reached this or not, when we are tapping the material, that let's say a free carbon is still floating on top of the mix. And if we let's say go on with the mixing time or increase the mixing speed, then after a certain period of time, which is significantly longer than the time for just pre-mixing in the wet application, we have a fully coated active material. And then we add the polymer binder, which is typically a PTFE. We mix this in. So at the end of this first step, we have a, let's say, homogeneous powder mix, which can be applied for a dry application already. When you're, let's say, hot rolling it directly onto the collector foil. Or we are now starting fibrillating the material by introducing higher shear forces and heating up the mix. And then we see after a certain period of time or certain temperature that we can form the material if we are pressing it. And depending on the kind of PTFE and the shear rate and the time, we have really a full plastic body which can be formed. And you could easily imagine that this material can be rolled out like a cake to form a freestanding film. The problem for this material is, of course, that the handling is quite complicated, the dosing is quite complicated. And this is where we are now starting to, let's say, form a material which can be conveyed. We are cooling the material, we are chopping the material inside of the machine, so that we, at the end, we have a structured mix which is incorporating fibrillated material, coated material, and which can be quite easily dosed and homogeneously distributed, for example, into a calendar system. Out of this, then you have, of course, a fibrillated or a film forming mechanism where you have a complete dry mix. Customers, of course, asking whether this is not only possible in lab scale, but also in large scale. So we was performing several times for customers already scale-up trials onto our 75-liter machine. This means from a 4-kilo batch up to an 80-kilo batch. We prolonged the mixing time a little bit because the cooling takes a little bit more time in a bigger machine than in a smaller machine. But at the end, we are ending up with exactly the same material properties. The same can be done on anode side. So here we see on the left side, this is a fibrillated mix in the large-scale pilot machine. We are chopping this machine product then into this dosable material. And out of this, we can then form, let's say, an elastic film with good flexibility. You see this already on the bending radiuses, that this film is, let's say, good, has a good inner adhesion. To summarize my presentation, you have seen that we have a simple and a smart process technology. We have significantly higher output performance compared to other mixing technology, especially like the PD mixer. We have highest flexibility in terms of raw materials and processing routes. This means, as you have seen, you can make wet, you can make semi-wet, you can make dry, you can make different dry routes. We have typically a very short batch time, just minutes instead of hours. We have an excellent scale-up capability, 90% less energy consumption in comparison to state-of-the-art technologies. This means also a significant CO2 emission reduction and higher sustainability. We have outstanding operating cost savings compared to traditional PD mixers, so that even if we would have a higher price, but we get the feedback from our customers that our price is absolutely competitive to PD mixers, even lower, you would have additional savings every year. We have Conti feeder technologies, which allows to continuously supply coating slurry to the coating line. We have significant less required space, means you have savings in infrastructure and building. We, Eirich, working as a turnkey solution provider, mainly, of course, not for the factory, but let's say everything from powder in to, let's say, processed electrode material to the downstream equipment like the coater or calendar. We have production experience since 2018, and the same machine is capable to produce a structured dry mix in the same machine. So to summarize it into one sentence, we have a highly sustainable mixing solution with maximum flexibility and upgrade capability for all types of electrode production. Thank you very much for listening. I'm now open to to answer your questions, and hope you will become the pioneer in electrode processing. Thank you very much.
Thank you. So we have a few questions in the inbox, and I will start directly with the first one. So first, you showed on slide 5 the different mixing steps and explained the hard kneading for slurry. If you have a battery system which is dry coated, how you deal with material which is damaged, modified under high shear rates?
Yeah, this is a good question. Typically, let's say if you have a nanoparticle which is properly dispersed and coated on the surface of the active material, it is really sticking there by electrostatic forces. It is not peeling off the material. But at the end, this is now then the point we can apply, or we can change the shear rates in our machine in the different phases. So if you then run the system, you have then to observe whether the typical shear rates are too high or good enough. And then you can make a study with different shear rates and to see what would be the critical shear rate until maybe particles may break, or until, let's say, you have then the effect that the coating would be removed on the surface.
Okay, thank you. Then the next question is about your automation strategy. Does modularization and the module automation via MTP already play a role? If not, what is your opinion about MTP?
I have now to ask the question, what does mean MTP? Never heard of this yet.
Okay, so dear participant, can you just add this information? Okay, model type package is MTP.
So let's say we have different modules, as you could already see on the let's say pictures from the UK PIC. This means one module is of course a mixer with all necessary equipment directly connected to the machine. Then we have typically a module, for example, for all liquid dosing and let's say liquid application. Means all the dosing system pump, let's say, incorporated into a module. The same is then for the vacuum systems, for example. We have modular systems for the tank systems with return pipes, integrated sensors, so that we can just communicate via Profibus system with our PLC. And then, of course, let's say, send the data by UPC-OA to the MES system. I hope this answers the question.
Okay, then the next one. From a process perspective, what are the main challenges in migrating from wet process to dry mixing process? How does it impact the coating calendaring process?
That's also a good question. So from, let's say, our point of view, and we're working also in let's say, research projects, First of all, we have, let's say, the way of coating is completely different because, let's say, wet coating is like putting paint on the wall. The dry coating, you have this powder which has to roll out and to form a film, which has to be laminated onto the collector wall. This means you don't have a coater. The calendars are typically looking in a, let's say, a little bit different than the typical calendar in the let's say wet electrode production. This means you need you can, if you have the Eirich mixer, you have the same mixer. We have a different extraction system out of the machine because we have to handle now powders instead of liquids. You would have a different, or you need the additional dosing system. You would have, of course, a different kind of calendar to form the electrode and to laminate it on the film. The slitting station is maybe exactly the same, and also then the vacuum drying, because mainly the way processing it into, or let's say applying it onto the collector foil is different. And the main challenges is a lack of experience and the lack of know-how. Of course, in wet application, let's say already since 1990, let's say 3 decades of knowledge is, let's say, accumulated, especially in Asia, of course. Everyone knows more or less how this operates, and also in big scale. While, let's say, dry application is a game changer. You can save significantly amounts of money in investment and also in operation. But the know-how level is still very poor, especially the recipe development, kinds of PTFE, and also how to really make electrodes that work, let's say, on long term in the cells.
Thank you. Then we have an additional question to the first one. Are you using only experimental procedures for the determination of the share rates, process parameters, or have you also digital approaches?
We have, or let's say, mainly we're working, of course, on base of experiments, because our customers will only trust us when they have the material, their own recipes in their hand, and they can make their own tests. We are working also together with companies, and we have shown this, for example, also on the Hannover Messe this year, together with Siemens, that we are using CFD simulations and virtual digital twins. But the question is how you can feed this and how you can validate this. At the end, you have to know, you need, let's say, long-term experience and know-how to validate the CFD simulation. Otherwise, it will just be colors for directors. And this is the challenge. So we see that our customers trust us in the best way. We have to make a test. They see, does it really takes just 15 or 20 minutes instead of hours, that we can make, instead of one test every 3 days, we can make 3-4 tests a day. And this is more convincing than any simulation, especially in this phase when you have to convince the customer to trust you that our technology will work.
Okay, thank you. Then we have one last question, and time flies. How precise are the technology specifications in these projects, and how important is scale-up testing under real conditions with battery material in the conceptual phase?
It's also a good question. When we were starting in 2009, we had just, of course, small lab machines, and we could show up, yes, we can do it in 20 minutes, but nobody was trusting us that the 20 minutes will work also in big scale. Then we started and developed a pilot machine, 75 liter, which is available for renting and also now in, let's say, in our test center. But we had then the chance to offer earlier and to realize earlier bigger scale machines. And we could show up that the scale up works really from the 5 liter to the 75 liter to the 500 liter machine without any problems. Of course, the customers are still hesitating somehow, and they are really convinced if they see to make a test in small scale, medium scale. This is typically, which let's say gives them the safety or security that the scale up will work. And we have still customers that say, oh, especially in front of the startup of a gigafactory, maybe the installation will not work properly. And here we have the chance, for example, like UK BIC, where our customers have already tested also in 1-by-1 scale in this facility to make sure that they have no, let's say, surprises during startup of a gigafactory. Unfortunately, and this is also our experience, we was significantly better than everyone was expecting. So even in the gigafactory scale, we are starting from the first batch. If our dosing system was properly adjusted in before, we are starting with an excellent quality from the first batch on.
So thank you very much for this very interesting presentation and answering all the questions. Dear participants, here also the same. If you have further questions to Dr. Gerl, please write us an email to pautech@nürnbergmesse.de and we will forward them to Dr. Gerl. Thank you very much.
Thank you very much.
And now, last but not least, I will hand over to Dr. Jennifer Burt from Malvern Panalytical and her talk on importance of particle size and shape analysis to improve battery performance. The stage is yours.
Thank you. Let me just share my screen. Great. Yes, so thank you for the opportunity to talk today. My name's Dr. Jennifer Burt and I'm an applications specialist at Malvern Panalytical, which is based in the UK. And we're a manufacturer and supplier of analytical instruments. So today I'm focusing on particle size and shape analysis and how that impacts battery performance. But we do also provide solutions such as X-ray diffraction and X-ray fluorescence equipment. So please do come and talk to us about your applications. We're always happy to discuss. So I'm going to start by just kind of going back to the structure of a lithium-ion battery. So this is the structure of a typical lithium-ion battery containing a liquid electrolyte. Typically, the anode is made of graphite, while the cathode is metal oxide, such as lithium cobalt oxide or lithium iron phosphate. And when external power is applied, there is an overvoltage, which forces the intercalation of lithium ions into the graphite anode. This increases the stacking distance of the graphite layers, which results in a potential energy increase. And then this is then released as electrical energy when the battery discharges. And it's worth noting that currently there's also a lot of research going into solid state batteries, where the flammable organic electrolyte is being replaced by a safer solid ceramic or polymer electrolyte. These typically use similar cathode materials to conventional lithium-ion batteries. And so today I'm going to show why measuring the particle size and shape of the cathode and anode materials used to manufacture lithium-ion batteries is so important. So each cathode material has a typical battery profile, which covers the 6 key requirements for a battery. So it needs a high energy density, which is how much energy the battery stores. It needs a high power density, which is the ability to deliver a high current. It needs to be safe to avoid issues like thermal runaway events. And then we also need to consider factors such as its performance, its lifespan, so how many times we can cycle it, its longevity, and of course cost. And on top of this, as always, sustainability is also really key. So battery technologies are evolving fast, which obviously presents both an opportunity as well as a challenge. So materials are changing all the time and new options are constantly being discovered. And the particle size and shape of these electrode materials, so both the well-established ones and these new ones that are coming through, will directly impact the battery profile. And hopefully over the next few slides, I'll show why this is the case. So first, let us look at the beginning of the process. So actually manufacturing the cathode powder from its precursor materials. So this slide shows a schematic of the cathode precursor preparation. Let me just get a laser pointer. So the precursor particles will evolve by nucleation and grow into primary particles. And then these primary particles will agglomerate together to form larger secondary particles. The size and shape of those particles are impacted by the process parameters. So if you increase the pH, you tend to get smaller and more spherical primary particles being produced. Similarly, increasing the mixing speed has a similar effect as well. And the result with smaller, more spherical particles is an increase in the tap density of the material. So The particle size in the precursor will determine the particle size of the final cathode material and its tap density. So now let's move on to looking at the final cathode materials. The particle size will be an important factor in how quickly you can charge the material and how effectively the particles will charge. So at the top, we have an image of a large particle where the different colors represent the active material, which is in blue, the bulk material, which may be inactive at a fast charge rate in green, and some electrolyte that's been degraded on the surface in yellow. So if the particle is too large, it may take too long to lithiate or delithiate, and you're not making full use of the material, particularly at fast charging rates. As the particles get smaller, they can charge and discharge faster due to their larger surface area to volume ratio, but they'll also suffer from a lot more electrolyte erosion at the surface of the particles, with this degradation increasing with cycling. So the desired particle size, apologies. So the desired particle size of the cathode material is therefore a balance somewhere in between. So generally, large particles will hold lots of lithium ions and they will have good specific energies, while the large surface area to volume ratio of the small particles enables lithium ions to be transferred between the electrolytes easily, so they can generate a lot of current, leading to high specific powers. So now, if we move from looking at single particles to particle size distributions, what we're looking at here in the graph to the right is the packing density versus the ratio between small and large particles. And what you can see is that at either end of the scale, where you either have just large particles or small particles, the packing density is lower than if you have a mixture of the larger and smaller particles. So a higher packing density will give you a higher bulk mass, which will result in a higher capacity. However, it's not quite that simple because we also need to have some interstitial space for the electrolyte to allow for the transport of ions. And therefore, it's somewhat some of a trade-off between these when we're optimizing the packing density. And it's not just that. So to produce the finished electrode, the electrode material and conductive additives are combined with the polymeric binder and solvent to form a slurry, which is then applied to a metal foil. So obviously the rheology of the slurry is important. And the particle morphology affects the slurry rheology, which will in turn affect the electrode production process. So in general, the smaller the particles you have, the higher the viscosity of the slurry, due to the increased particle-particle interactions. And this is more pronounced at lower shear rates, as shown here. And then as well as that, generally broader size distributions will reduce the viscosity of a slurry, essentially because you're increasing the maximum packing fraction. So if you increase the volume into which the particles can move more easily. So look at the bottom graph where we've plotted viscosity against the volume fraction of particles. If you have a monomodal distribution, then you'll have a higher viscosity for a given solid loading compared to if you have more variation in the particle size distribution, where we'll see lower viscosities. So this slurry is then applied to the metal foil to ideally form a nice uniform electrode film. So this means we can also look at the effects of the particle morphology on the coating quality. So as particles get smaller, they're more likely to stick together, as shown by the graph on the right. So this means that the more fine material you have, the more likely you are going to get agglomerates. So this increases the chances of getting inhomogeneities in the slurry film, which has potential to lead to greater variability in the ion transfer rates and the charge discharge rates, which ultimately is going to impact the battery lifespan. So we've talked a lot about size, but particle shape is also important. So going back to packing density, irregularly shaped particles can reduce the packing density, which will increase the interstitial space for the electrolyte between the particles, which increases the ion transfer rate. However, irregular shapes can cause particle friction and interlocking, which can increase the viscosity of the slurry, which impacts its application. Generally, more spherical particle morphologies are preferred due to their ease and packing. So that should have hopefully given a few examples of why we want to measure particle size and particle shape, and where it's important, where it's influencing the battery production processes and the battery performance. So now we'll look at how we can measure and monitor the particle size of electrode materials using laser diffraction. So the Maschinenfabrik 3000 is the world's leading particle size analyzer for rapid and reliable particle size measurements. It covers a very wide particle size range, so we can go from 10 nanometers up to 3.5 millimeters, and this uses a single optical measurement path. Both wet and dry analysis modes are available, so this means that we're able to measure powders, dispersions, and emulsions, and it also has excellent chemical compatibility, which allows us to handle solvents such as NMP. So how does it work? So in laser diffraction, we measure the light scattering pattern produced by particles illuminated in the laser beam. If we have large particles, we get mainly high intensity scattering over small angles. So this results in a ring pattern like the one shown here. And then as the particles get smaller, the angle of scattering gets wider and the intensity gets lower. And this then results in a much more diffuse scattering as shown here. So what we're doing with laser diffraction is we're measuring the intensity of scattered light as a function of angle. So now I'm going to look at some examples of battery materials that have been measured on the Maschinenfabrik 3000. And we're going to look at both the particle size distributions as well as the dispersion trends, which we use to investigate the state of dispersion of the material as we measure it on the Maschinenfabrik. So first, here we have a lithium cobalt oxide powder that's been dispersed in water with the addition of a surfactant to help wet the powder. So from the trend graph, you can see that the particle size distribution is stable both before, during, and after the application of ultrasound, suggesting that the sample is well dispersed without the need to input extra energy. If we then look at the particle size distribution, we can see that it's monomodal, and the particle sizes are relatively large for a cathode material, so this should be giving us higher specific energies. For this lithium iron phosphate material, which we've also measured in water with a surfactant, we can see that we definitely need ultrasound to disperse this material. So at the beginning, before the application of ultrasound, we have quite a large material, and that's highly agglomerated, and this takes several minutes of ultrasound to disperse before we get to the end where we have a fairly stable percentiles. So the final distribution that we end up with for this material is smaller than the previous example, and we can see that it clearly has a broader size distribution. So this is going to impact the exposed surface areas and the packing density of the material, and likely give us higher specific powers. And then finally, here we're looking at an anode material, so graphite, which again has been successfully dispersed in water with a surfactant. So again, the dispersion is very stable. We don't need ultrasound to disperse this material. And this sample has a very narrow monomodal distribution, which is obviously going to impact the slurry viscosity for the reasons we discussed earlier. So that's how so we can use the Maschinenfabrik 3000 to measure particle size. It's very fast, it's very reliable, it gives us, it's got a high throughput, we can do hundreds of measurements in a day. In our final section, we're going to look at automated image analysis on the Morphology 4, and this enables us to measure both particle size and particle shape. So as we discussed earlier, particle shape also has an impact on battery production processes. So image analysis can tell you several things. So it can tell you if your material is mostly single particles or whether there's agglomerates. It can tell you whether your material is regular in shape or maybe whether it's more elongated. It can tell you something about the surface of your particles, so whether you've got rough particles or smooth particles, which is obviously going to impact surface area. And it can also tell us something about how light passes through the particles, so whether they're dark or light. And traditionally, particle shape would be measured using manual microscopy, but this is very time consuming and susceptible to user bias. So automated image analysis allows the rapid measurement of thousands of particles to provide non-subjective statistical analysis of particle size and shape distributions. But how does this work? Well, in automated image analysis, we automate the capture of images of dispersed particles. So we'll take images of hundreds of thousands of frames, and from this you'll get tens of thousands of individual particle images. From these images, we can extract size and shape data, so things like the circular equivalent diameter, length, width, circularity, elongation, convexity, and we have that for each individual particle. But then we can also, with that, also build particle size and shape distributions and use the tools within the software, such as scattergrams and comparison tabs, to compare these distributions and to produce results. So there's 4 key stages to a morphological measurement. The first stage is dispersing the sample, where we want a good dispersion of well-separated particles. And we have a range of different dry and wet accessories available, which allows us to look at our samples either as dry powders, as slurries, as suspensions. We can also look at samples on filters. These all can be analyzed. Next, the sample is automatically scanned, and segmentation algorithms are used to separate images of the particles from the background. These images are then processed, where a vast array of size and shape parameters are calculated for every particle in the sample. And then finally, the results are reported for each particle, along with statistical results for the whole sample. So now let's look at an example of a series of cathode materials which were measured on the morphology 4. So here we have 3 lithium manganese iron phosphate cathode materials, and these had differing ratios of manganese to iron. So on the left, we have an 80-20, in the middle, we have 40-60, and then on the right, we have just iron phosphate. So the purpose of this study was to understand the impact of the manganese on the particle size and shape, and then take this back to powder properties. So each was dispersed under the same conditions using the integrated sample dispersion unit of the morphology 4, and automated image analysis was performed at 50 times magnification. And for each material, tens of thousands of particles were measured, which gave us good statistical significance. So the primary output of image analysis is a number-based distribution, which we can see here on the left. Hopefully what you can see is that there is a small shift towards smaller particle sizes as we increase the manganese content of the material, but you can probably see from these percentiles, these differences are fairly minor. We are also able to transform to a volume-based distribution, like here, what we've shown on the right, which shows that by volume, these materials are very similar. We can then compare the volume-weighted distribution, which we measured on the morphology 4, shown again here on the right, to that measured on the mass size of 3000, so using laser diffraction. And what we can see here is that we have very good comparability between the 2 techniques. What is interesting, though, is when we look at particle shape and more specifically elongation. So with the elongation, a value closer to 1 means a more elongated particle. So looking at the undersized chart here, we've plotting the elongation for the 3 samples. We can see that overall elongation increases with an increasing load of manganese. So from the purely iron to the 40-60 to the 80-20. And hopefully what you can also see is that we got good reproducibility from 2 separately measured dispersions of the same material. Though obviously we'd ideally look to doing more repeats just to double check that. And then we can also look in even more detail because we have those particle images available and all the associated information with them. So we can look at, you can explore these differences in even more detail by classifying the particles in the software. So here we looked at classifying the particles as either spherical, slightly irregular, elongated, or very irregular. Each particle would fall into one of these four classes. So you can see, for example, for the spherical, the particle, to be classed as spherical, the particle would have to have a very high sensitivity circularity and an elongation below 0.25. And on the right, you can see some example particle images for the particles that fell into each class. And then because we've done this, and we've done this for each of the materials, we can then compare the percentage of particles that fall into each class. So here we've shown the number-based classification chart on the left and the volume-based classification chart on the right. And comparing these three materials shows that with increasing manganese content, so going from the blue to the green to the red line, we're seeing more elongated and irregular shaped particles in the material. So what we would then do is consider if these differences in the particle shape are affecting the properties of the powders, such as the packing density and flowability of the materials, and also consider the impact that that might have on battery production. So thank you for listening. Do we have any questions?
So thank you very much, Jennifer. So I just check the inbox. Okay, so we have a question here. Can you go into more detail on how particle size and shape is important for solid state batteries?
Yes, so yes, most of the examples I was showing was more the traditional liquid electrolyte batteries, but basically in any process where you're looking at packing density, you're looking at flowability of materials, you're looking at reaction rates, this is where particle size and shape is going to be important. And for a solid state battery where you've replaced the liquid electrolyte with a solid electrolyte, the particle size ratio between the active cathode material and the solid electrolyte is important. And I think studies have shown that the particle size of the cathode material should be bigger than that of the solid electrolyte to give you higher energy densities.
Okay, thank you. Then we have another question. It's a bit a longer text regarding the correlation between particle size and rheology. Can we always say that high slurry viscosity always correlates with low particle size after mixing? How would this affect the density of the slurry?
That's a good question. So we are, sorry, could you repeat the question?
Yes, of course, no problem. So regarding the correlation between particle size and rheology, can we always say that high slurry viscosity always correlates with low particle size after mixing? How would this affect the density of the slurry?
So yes, so obviously particle size, we're kind of talking more about the particle size distribution. So if you have a mixture of larger and smaller materials, then you'll basically be able to pack more material in, so increase the packing density, and this will obviously have an effect on the viscosity of the slurry, as we discussed, as I showed on my slide. What we're doing with particle sizing is we're looking to with these particle size analyses is kind of looking to explain the slurry rheology that we're seeing. We're obviously not directly measuring the viscosity of the slurries here.
Okay, thank you. Then we've got another question. How can you differentiate between agglomerates and single particles?
So that's another great question. So in laser diffraction with the masticizer, for example, we would be looking at the state of dispersion. So that's where we would use the ultrasound, for example, to investigate whether a material is agglomerated. If we apply energy to the dispersion, does the particle size decrease because we're successfully breaking up agglomerates? We'd also want to check that we weren't actually breaking apart the particles, which we could do with an ultrasound titration, for example. We can obviously do something similar with image analysis as well, but obviously with image analysis, we're also getting images of the individual particles. So we can actually look at those particle images and look at some of the parameters that we've measured, such as solidity, which kind of looks at how solid the particle is essentially. So particles with a lower solidity, for example, are more likely, agglomerates are more likely to have a lower solidity than single particles, for example. So we can start to separate the different particle types that way.
Okay, thank you very much for the explanation and also for this very interesting presentation, Jennifer.
Thank you.
So dear participants, if you have further questions to Jennifer, please write us an email at powtech@nürnbergmesse.de. We will forward them to Jennifer as soon as possible then. So thank you very much for joining us today at our virtual talk. Upcoming dates and topics of the virtual talk series can be found on powtech.de or follow us on LinkedIn. It's the site Powtech Nürnberg. Stay tuned and feel free to join us again. And yeah, we're also much looking forward to welcoming all of you at Powtech and Partech this year in September from 26 to 28. Have a nice day and see you soon. Thank you very much. Bye-bye.